Hey guys, I'm going to go over the pre-lab for the rubber stopper lab. Okay, so just to start off, just some FNet review. What can't go on a free body diagram? On a free body diagram, you could never have FNet, make this a little thicker, or FC for centripetal, because that's also a net force. You can't have acceleration, you can't have velocity, even though those are vectors, they don't go on a free body diagram because they're not forces. And then you also can't have components because components aren't real. They're just a tool that helps us to solve things. What are our three FNets? We have FNet equals 0, we have FNet equals MA, and we have FNet equals MAC, which we write as MV squared over R. In what direction is centripetal force and circular motion? It is always center seeking. So towards the center, or you can think of it as radially inward. So in the direction of the radius, but towards the center. What direction is centripetal acceleration? Well, force and acceleration always agree. So they're always in the same direction, the net force and the acceleration. So it's going to also be towards the center or radially inward. What direction is velocity? As something goes around in a circle, its velocity is always trying to continue in the direction it's going. It's always trying to go in a straight line. Inertia is dragging it that way. So we would say tangent to the circle, or you could say tangential. All right, two equations for weight. I think by the time we do this lab, we won't have the second equation yet, but it shows up later in the notes in this section. If we're near the surface of the Earth or near the surface of any large mass, it's just m times g. But we also have the attraction of every other mass in the universe. And this one is Fg, with the big G, is equal to big G, which is a constant, multiplied by the product of the two masses over the distance between their centers squared. And it turns out that little g for Earth we get by putting in the mass of the Earth, the 5.98 times 10 to the 24th, and the radius of the Earth, 6.36 times 10 to the 6 meters, and squaring it and multiplying by this universal constant, which is 6.67 times 10 to the negative 11th Newton meter squared divided by a kilogram squared. All right, I'm going to clear the ink and scroll this up. All right, so we're going to do a horizontal circle in this lab, but the pre-lab I'm going to do a vertical circle practice problem with you. So we're swinging a 2 kilogram mass in a vertical circle. When is the tension the greatest? If we're looking at our circle here and we do our free body diagram, I have a fruit fly flying around at me because I'm in the light. When we're at the bottom, the weight is down and the tension is up. And we're at the top, the weight is down and the tension is down. So when you're at the bottom, the tension has to do two things. It has to lift the weight and it has to turn it. So it's going to be the greatest at the bottom. That's when weight is working the most against the tension. When it's at the top, we don't even have to have tension based on how fast we're going. So the weight is helping to turn us, and we don't have to lift it. So it's the least at the top. Centrifugal force, this idea of when we're turning, something's throwing us out. This is fictitious because it's really just inertia. It's really just an object's tendency to remain going straight, to keep going in the way it was going. All right, so let's do a problem. So we're going to have a man swinging a 2-meter long rope in a vertical circle. Hopefully he's standing on top of something because that's going to be a very long circle, right? On one end of the rope is a 3.5 kilogram mass. Each circle takes 1.5 seconds. What's the tension in the string at the lowest point? So there must be some tower with a man, and he's swinging the rope down and up. So I'm going to draw this path. I'm going to look at the lowest point here. And at this lowest point, the forces that are on it, like we said before, was tension up and mg down. The tension should be longer than the weight because it is both balancing the weight and turning it. All right, so I recognize this as circular motion. I'm going to say that F net equals mv squared over r. And then our rules, which are new, is we take the forces towards the center minus away. You don't have to have a force away, but you have to have one towards. Something has to be turning it. So this is going to be T minus mg equals mv squared over r. So T is going to be equal to mv squared over r plus mg. This equation is just like I said. The tension has to both turn it, which represents this force, and lift it, which represents this force. All right, I don't know the velocity, but I do know how long it takes to go around for one time around. If you remember, this is our period. So the time it takes for one loop around. And our velocity is going to be equal to our circumference, which is 2 pi r divided by this period, that's 1.5 seconds. I'm not going to put in capital T because unfortunately we already have a capital T from tension. I don't want to confuse you. So I'm going to have 2 pi times 2 meters over 1.5 seconds. And this is going to give us what our velocity is. So I have 2 times pi divided by 1.5. So 8.4. So now I can substitute this in. I know my mass is 3.5. We calculated a velocity that was 8.4. That's squared. Our radius is 2 meters, and I'm adding this to the weight of the 3.5 kilogram mass. A 3.5 kilogram mass is going to weigh 35 newtons. Just multiply it by 10, right? So and I got 158.5. Now, what we do in the lab, it's going to be much simpler because the only thing that's going to be turning it is tension. There's no other force in the direction that it's turning because we're going to try to do a horizontal circle. All right, I'm going to clear the ink and scroll down and do the last part, a little bit of review. The string is going to break where the tension is the greatest, which is at the lowest point, and we're going to have a horizontal launch problem. All right, so the lowest point in our problem is 1 meters above the ground. If the rope breaks at that lowest point, how far from the man will the mass land? So in this vertical circle, we're breaking at this point, and it's going 8.4 meters per second. It's going to fall down 1 meter. So what I'm going to do is I'm going to make a y direction chart to find out how long it's in the air, and then an x direction chart to find out how far it goes horizontally, what our range would be. So my y direction chart, if you remember, our initial velocity in horizontal launch is always 0. Our acceleration for a projectile is always -10. In this case, our displacement is 1. Sorry, -1, because it starts at a certain height and it finishes 1 meter lower. We take down to be negative. All right, so looking at our kinematics equation that we use the most, we can see that this is going to cancel out. We start with no initial velocity. The velocity is all sideways at this point. All right, so I'm going to get t by itself. I'm going to multiply by 2. I'm going to divide by my acceleration, and I'm going to square root. And so I have 2 times -1 divided by -10. Remember how important it was in this section that we have signs, because you don't want to be trying to divide a negative by a positive and then taking the square root. And this is going to be 0.445. So it is, oh, that's way off. All right, in our x direction, our initial velocity and our final velocity are the same. Our assumption is there's no air resistance unless they say there is. We want to find the range, and the time is the same. So I can say that x minus x naught equals v naught t plus 1/2 at squared. But since a is 0, that all cancels. And so this is going to be 8.4 meters per second times 0.45 seconds. I think it's, I shouldn't guess, it's been a while since I did this problem. So 3.8. All right, good luck on the lab. Try to spin it so that it's as horizontal as possible. And when you're spinning it, you want the bottom part on the glass to be just below the glass, but not against it. So you're trying to spin it just fast enough that you're lifting that weight up, and you're keeping the radius 0.5. So they're measured out so that thing goes right below the glass when it's at 0.5.